welcome to today's Shopfloor Data Session, OPC UA for Industrial Joining Technologies, or short IJT. It's about the specifications OPC 40450 and OPC 40451. And I'm very happy to have these two experts here with me today. We have Bernd Heitzmann from the VDMA and Mohit Agarwal from Atlas Copco. And I would ask you now to introduce yourself, please, to our participants.
Thank you, Heiko. Yeah, my name is Bernd Heitzmann. I'm from the VDMA, taking care about the integrated assembly solutions, assembly, roboting systems, as well as gripping and tightening systems. I support the OPC UA working group, and that should be for the moment. And I would pass to Mohit.
Thanks, Heiko. Thanks, Bernd. I'm Mohit Agarwal. I'm Principal Engineer at Atlas Copco, Sweden, and I'm also Technical Editor of the companion specifications for joining and tightening systems. And now we will go ahead with the agenda. So today we will discuss about what is industrial joining technologies. And then we will go through about the use cases. What are the use cases which are covered as part of the specification? And then we will dig deeper into the technical models. After that, we also have a complete reference implementation of an OPC UA server and OPC UA client, which is published in GitHub. We will go through briefly with the demonstration. So let us get started. Industrial joining technologies, and what is it, and an overview of what exactly or what type of problem statement it is solving. So a brief history. In 2018 and 2019 timeframe, OPC UA exists for more than a decade. But in 2018 and 2019 timeframe, we received requests on whether we have a companion specification for tightening systems. So we collaborated with OPC Foundation and VDMA, multiple organizations together, and figured, okay, there is no companion information models for tightening systems. So we met for the first time in May 2019, and multiple tightening vendors have participated in that meeting along in the VDMA office. And the discussion was, how do we define that? But during that discussion, we wanted to cover a broader vision. Why are we only defining models for tightening? There are a lot of commonalities with other joining technologies as well, such as gluing, riveting, floor drill fastening, etc. So therein, we discussed and agreed and created a working group called Industrial Joining Technologies. So what we see on the screen is the taxonomy of the working group, and we created a lot of joining technologies and placeholders here. But we had to start at some point. So we started the technical work in 2019 only on the tightening use cases. And then we also wanted to cover or be in the market as fast as possible to evaluate whether the models which we have defined works for the industry. So in October 2021, we published a first minimal version of tightening specification. And we evaluated, demonstrated that in different public fairs like Automatica and so on. And then in the parallel, we started working on the joining specification. We collaborated with multiple harmonization groups. And that's where we have come up with a new joining specification this year. So I will go through all the details step by step in the subsequent slides. So as I mentioned here, now this year in March 2024, we published two different specifications. One is OPC 40450 base specification, which is common for all the joining technologies. And then we have published a second version of tightening specification where most of the models defined in tightening were extended and generalized and moved to the joining specification. So we have published both the specifications now, and it is publicly available with a reference implementation. So this is about industrial joining technologies and the taxonomy. But then who are the working group members? These are the working group members who meet on regular basis. So we have weekly or bi-weekly telecom meetings, and we meet once in 3 to 4 months face-to-face and continuously work on the information models, improvements, and any other use case which is of interest. Apart from the core working group members, what we see here, we also do a regular updates to several customers and stakeholders. So we organize separate customer meetings and stakeholder meetings once in 4 to 6 months and present the status, get the feedback, and try to incorporate those feedback in the specification work. I'll move to the next slide. Most of the content here I have described. As I mentioned, we started this working group in May 2019. And October 2021 was the first milestone where we published the first version of specification. And then we continuously worked on both tightening and a base joining specification. And now we have a formal specification for joining systems and tightening systems. So this is about an overview about the working group. The next slide visualizes what amount of reuse we have done. So we have not reinvented everything. The main or the core problem in OPC UA is interoperability. Now, for joining and tightening, if we start defining our own models or if we start reinventing things, then again, interoperability will be difficult. So that's where we have reused specifications like device integration, DI, asset management basics, machinery and machinery result. And moving forward, there will be other base specifications or harmonized specifications, which we would be using in the next versions. So this is just to mention that a lot of models are reused from parent or base specifications. So far, we have covered an overview about the working group, what technologies we are planning to cover and have covered so far, and how much of reuse we have done from other companion specification groups. Now from the next slide, we will cover about the technical use cases. What are the use cases which we have defined in the specification? So when we first worked on the tightening specification release 1, the primary use cases were asset management, basically getting an overview of what assets are available within a station, within a line, and so on, and how do we identify the assets like serial number, manufacturer, etc. And then the second use case was tightening result. When we use a tightening tool and perform a joining operation or a tightening operation, there is an outcome generated. There are a set of values like torque values, angle values, and so on, which are generated. And those are covered as part of tightening result. And that is a very core use case from the joining domain. The third and fourth use case, condition monitoring and basic events, we have covered only to a minimal extent when we did the first version. So what is condition monitoring? Getting to know the health of the device, like temperature, device health, etc. And basic event, we just defined a simple event with a string placeholder. So these were the use cases which were covered in the October 2021 release. But then we had more use cases to make it useful to the industry. How did we solve that? In the release 2, we covered additional use cases. In result management, earlier, we only covered results with respect to a single tightening. I have a tool, I perform a tightening on a single bolt, an outcome is generated and that is reported. But then in a factory, we can do an assembly of a wheel where 5 different bolts are tightened together. We can assemble a seat and several complex parts. And then there can be consolidated results. There can be a batch result. There can be a synchronized result. There can be a complex job result. Is my assembly of the car completely successful or not? So those additional use cases were defined in the release 2. Event management, here we have defined a very comprehensive type of filter criteria. Earlier, we just had a string placeholder. Any event will contain a string message, which will be used to identify what this event is about. But from a client's perspective or the user's perspective, it is difficult to filter them. So we have defined a standardized payload in events now, and also a set of filter criteria which can be utilized from the client's perspective. And the third use case, which is very important again, is a control mechanism. In tightening domain, this use case is called as commands. Basically, it is a set of methods which can be used by external clients to communicate with the underlying joining system. Somebody would like to select a program. Somebody would like to start a program. Somebody want to get a list of processes or programs available, lock the tool, and so on. So we have defined more than 40 different commands in the specification. The last use case which we are seeing is a futuristic use case called joint management. In a traditional approach, users select a specific program where if there are 10 different programs in a tightening controller, the operator or the user needs to know which program is suitable for this specific bolt. But with respect to joint management, the user can just provide the joint ID or the bolt identification, and tightening system will take care on which process is suitable to perform tightening on that bolt. So with this, we are enabling an easier option to the clients where they can just provide the joint identification and some prerequisite data, and tightening system will take care about the suitable tightening process or the joining process. So these are the high-level use cases which are covered. Now we will go through the technical overview of the models. When I say technical overview, how did we model each of these use cases? So joining system overview. This is the first use case. From an OPC UA client's perspective, this is considered as an entry point. So there is a joining system which contains different building blocks like asset management, result management, joining process management, and joint management. And this joining system is not an asset, it is a collection of building blocks. So it's a top-level structure which helps in visualizing and organizing various use cases in a given joining system. So this is a primary common interface or the standard entry point. Now we can dig into each of these building blocks. Let us go through asset management. So in asset management, we have defined the most commonly used assets in a joining system. What are those? Those are like controller, tool, servo drive, feeder, battery, cable, etc. So these are most commonly used assets. And also we have defined a generic asset called subcomponent, which can be used for any other miscellaneous assets. For example, if we want to model a 5G radio module or so on, we can use subcomponent and so on. And also, we have utilized concept of interfaces and add-ins from OPC UA, which help in defining the models using open modeling approach. What does it mean? In future, if there is an expert group which comes in and defines a very comprehensive model for memory device, can we integrate or can we merge or can we utilize that? Yes, because we have used the concept of add-ins and interfaces. It is a matter of integrating any additional models and then defining set of additional profiles and conformance units. With that, our models with respect to asset management are pretty flexible. And one more important thing is we reuse base specifications like machinery building blocks and asset management basics. And one more point is we have provided various examples in the specification All these assets can be used in different combinations. In a joining system, there can be a handheld system where we have a controller with a cable tool connected and maybe 5 different wireless or battery tools. That can be modeled. It can also be used to model a fixed system where there are 8 spindles connected to 8 tools and a central controller. So different options are possible using the current model. Let us go through the next slide where it visualizes the overview of how it looks in OPC UA. This image is a bit small, but in the specification it is much more clearer. All these assets we have defined. As I mentioned, we used open modeling approach and everything is base object type where we have defined interfaces and the respective rules. The key point in this slide is this common data. Each asset will have common information like identification and operation counters. And these are completely reused from machinery building block specification. And then the asset can have maintenance information, health information, and so on. In future, if parent specifications are extended and new use cases are handled, we just have to link existing asset models. So with that, it will not be a breaking change. This covers an overview about asset management. The next use case is result management. So we discussed about asset management. We discussed about the reuse of base specifications like machinery building blocks, asset management basics. With respect to results, again, we reuse a base specification called machinery result transfer. So what is the result? Whenever we perform a joining operation, there is a set of measurement values and set of graphs or curve values which are generated. And those are encapsulated into 2 different elements. One is the metadata, which will consist of identification of the result, timestamp, status, whether it is okay, not okay, and so on. And there is a list of metadata which is defined. The orange color blocks which we see here are from machinery result transfer. And we have reused that and extended it. So in the joining specification, we extend the metadata and reuse the content. And what did we define in the joining specification? We have defined concrete structures of what can be populated inside result content. There are different options which can be populated, and we have defined those using the simple structures in the specification. What are those options? So every result will have set of metadata which is defined by common set of properties. But then the content is dynamic because content is a base data type from the machinery result transfer specification. Based on the configuration, the content can point to a single result where we are performing a single tightening. It can point to a batch result where we perform a tightening of 4 or 5 bolts in a sequential way, or it can be a job result and so on. So with this, we have defined different examples, different rules with the help of conformance units, and provided concrete server implementation example and client implementation examples and how to visualize them. So this talks about the classification, result classification, and what are the use cases covered with respect to results. In the next slide, we will just dig down into how the actual content will look like. So what is the content when we talk about a single result? When it is a job result or a batch result, it is just a collection of these single results together. So if we dig down into the single result, it will have 3 primary elements called overall values, errors, and step results. Overall values, if we consider a program which contains 4 steps, there can be common values reported for the program, like the maximum time taken for execution of all the steps. Those can be reported as part of overall values. If there are 4 steps, each step can report different values. Each step will have a torque value or an angle value or a time value, etc. So all those are encapsulated as part of step results. Similarly, in the joining domain, there are traces generated. What is a trace? Whenever we perform a tightening, for example, a list of torque values, maybe around 500 to 1,000 different torque values will be there. And those are reported as part of trace, what we see here. So with this, it covers the traditional use case, which is managed using other proprietary protocols in different ways from different vendors. So with OPC UA, the handling of result is normalized and generalized, and it provides a standard interface from the consumer perspective. So this is an example of how a single result would look like. The next slide describes a simple example on what is the possibility of combination of results within a given system. In this example, this is just an example. The current result model can cover various levels of nested hierarchy or a flight hierarchy. Now, if we say the top level result is a complete result of the car, for example, and that contains sub-processes which generate sub-results. So we can model all these sub-results and group them together as a big chunk of a primary result, and that can be reported. Then there can be additional technical use cases like, okay, but if it is a too large result, are we going to send the complete result, including traces for each sub-result in a single message? Yes and no. It is completely dependent upon the configuration. The specification supports both. As we see here in the case one, we can send, if it is a small parent result, we can send a batch result which contains 5 different single results inside it in a single message. But if there is a need from a system where we would like to get all these results independently and later link them together, that is also possible. So we have enough metadata in each of these result boxes or result objects where we can link parent and child results. So depending upon the use cases, both the options are supported by the specification. So with this, we have covered asset management use case and result management use case. Now we'll go through the event management use case. So in event management, the IJT companion standard defines 2 primary objects. One is an event, one is the respective condition. If the system needs a transient information, an event can be used. If a system needs an acknowledgeable information or an object with a state associated, then a condition can be used. The key part here is the payload from the IJT companion standard. So we have defined a standardized payload. It also uses the base properties which come from the OPC UA base, from base event type or acknowledgeable condition type. But from joining system perspective, this associated entities is of importance. For example, if you want to send an event related to tool disconnected, then the message will contain tool disconnected, but this associated entities will contain the identifier of the asset with respect to this event. And similarly, if you want to report a temperature high event, these reported values can contain the temperature value, including current and previous value, so that the event and the event payload are self-contained. We get enough information from the client's perspective to process it, and identifier of different objects like devices and so on can be queried and linked, so that processing will become easy. This is one aspect, the payload of the event. The second aspect is the filtering. In OPC UA, there is a concept called condition classes. I do not have time to explain condition classes concept in detail, but how condition classes are used is to filter thousands of events can be reported from a given system. But how will client know which event is of importance? If you consider an example, tool disconnected. In this case, condition class can be set as system condition class and condition subclass can be set as asset disconnected. So client can subscribe and filter events with a condition subclass equal to asset disconnected. With that, there can be filtering applied based on the use case. And on the right side, if we see, we have defined the various type of filters within the IJT specification. Left side are the classes defined from the base specifications, and the combinations can be used. So we have provided a detailed example in the annexure sections to describe on how to use them. So with this, we cover event management use cases where it involves two different things. One is a standardized payload from the joining system, and second part is different type of filters from the joining system. The next use case is joining process management. This is also a very important use case. As I have described the result model, we can model a very complex result in a nested hierarchy way or in a flat way. If we consider or visualize this result model, we also have defined the joining process, and it matches exactly with the result model. The joining process will also have a metadata, and then it can also have a content where a single program will generate a single result, a batch configuration can generate a batch result, a joining job can result a job result, and so on. But one important point here is we did not standardize the content of the joining process yet, because it is so complex and different configurations are there, and those use cases can be discussed and defined in the next version of the specification. But we have defined set of APIs to manage the joining process, which I will go through in the subsequent slides. Then comes the last technical use case, which is joint management. As this is the first time we are introducing this concept, and many of the end users we talk to are interested in this because so far it is available in bits and pieces. The traditional way of managing a joining system is by selecting a specific process where it involves domain expertise. But over a period of time, we would like to provide an option to the users where they can just provide the bolt identification or the joint identification, and automatically the respective process is selected and executed. So with respect to joint model, we have defined simple objects called joint, which will know what is the respective program to be executed. It will have a reference to a design. What is a design? For example, residual torque of the joint, some properties or material information or material properties of the joint, and so on. And then the design can have a link to one or more joint components. For example, when we perform a joining operation, it is assembling two different parts. It can involve multiple bolts or screws or rivets together. So if we want to provide that information, it is possible to provide using the joint component model. So this is the first time we are introducing joint management in a standardized way, and this will have additional improvements based on the feedback we receive. With this, we cover primary use cases which are defined in the joining system specification. And then this slide describes about the set of methods. I was talking about commands, use case, and so on, right? So we have defined around 40 plus commands for different use cases. The left side is about the commands related to asset management, and then result management commands, which are inherited from the machinery result transfer specification. And joining process management commands, like in tightening domain, we might have heard about increment batch, decrement batch, reset batch, and so on. Those all can be covered using the set of commands defined here. And similarly, we have defined commands for joint management, where somebody can send the joint information to the system. And in the next operation, they can just say, select this specific joint, and so on. So that completely covers the technical use cases. And the last slide is about the certification overview. OPC UA is very comprehensive. Many times it is not easy to go through each model and understand what is needed from the joining system perspective. That's where OPC UA and base specifications provide a concept called profiles, facets, and conformance units. I cannot describe them in detail in this meeting because that is a completely broader topic. But from joining system perspective, we have defined simple profiles where from a client's perspective, you can say, okay, tightening tool provider should at least support one of these primary profiles, either basic profile or a general profile. And then you can check mark what are the features. We have given independent selectable features. You can validate or request a specific tightening vendor that these are the features which are of interest to you. So we have defined all these profiles in detail, and we will soon define the respective test cases and so on over a period of time. So that covers the presentation part. Now I will give a simple demonstration. The links and references will be available in the presentation, and the presentation, as Heiko mentioned, will be shared with everyone. I will end this slideshow and show the demonstration. So let me just first explain. This is the joining system specification. It has all the examples, and specifically I request everyone to go through the annexure sections. We have tried our best to define visual examples to help everyone understand how these models can be used. With respect to the demonstration, we also have publicly available GitHub where we have provided sample OPC UA server and OPC UA clients, and these links are available in the presentation. So if we see here, sorry, the server is terminated. I'm sorry for that. So now I have an OPC UA server implemented, a demo server implemented for the full specification. As I explained, this is the primary entry point, joining system type. So I have given the browse name as tightening system. As I mentioned, the building blocks like asset management are available, where we can visualize all the possible assets like tool, tightening tool. There can be one or more tools or one or more controllers, one or more cables, etc. All these assets can be linked with each other using a respective references like associated with and so on. Then similarly, we have joining process management and the respective commands, joint management. Because this is simulation, we have not implemented all the methods because in simulation it's difficult to do an actual operation, but there are more than 10 different commands for joint management. Then one of the important topics is the result. With respect to result management, from machinery result transfer, which is the base specification, a client can get access to result in 3 different ways. One is using the result variable in the address space. Somebody can drag and drop to the result, the data access view, or subscribe to the data point. Or someone can subscribe to the event with respect to result, and client will receive the respective result event with the same payload. And also, if somebody would like to get an older result or want to get the result using a method call, that is possible. So there are 3 different ways to access the result. So in this demo example, the key point is we have provided simulation options. So we have provided simulation of different type of results. Let me try to simulate a result. I will simulate a result with multiple steps and include traces in that. I will call it done. And so if you see here, it generates a result. This is the metadata. The most relevant metadata is set here. And result content contains a list of steps. It contains 4 steps. Each step contains different set of values and so on. I don't want to go into each detail about each property because it will not be very clear. If I talk about now, it will be too much of time. But I'm just giving an overview on a complete example. Somebody who is interested can just download this from the GitHub and play around with this simulator. So we report everything which is needed with respect to step results, traces, and so on. Apart from results, we also have provided options to simulate different type of events. So if you see here, currently 6 different types of events can be simulated. I will call this tool connected event, and maybe I will simulate a tool enabled event, and maybe asset temperature event. So if you see here, tool enabled event. The key point here is about the condition classes. These are helpful to know what is the type of event, system condition class and asset enabled condition class. So clients can figure out what exactly this event is about. And then if you see here, this associated entities will provide the respective identifier. So it gives the product instance URI of the asset. So if we say tool enabled event, it will provide the identifier of the tool. It will provide the respective filter which can be utilized to process the respective events. Similarly, if we talk about tool asset temperature overheat, we have similar things like the identifier of the asset, and then condition classes are available, like hardware, it's a hardware issue. It is a violation of a threshold, and it's also an error. So different condition classes are added. But one important thing is we also report the values. So temperature value, what was the current value, the low limit, etc. And there are different combination of events which can be generated. So we have simulation for results, we have simulations for events, and as you see here, we have the simulation for each of the asset. In this view, I only have dragged and dropped controller information. So we have controller, battery, and so on. So I have dragged and dropped the controller properties, and some simulated data is populated here. And just to repeat, this is available for free for everyone. We also have provided a web client which you can try. It will give visual graphical presentation of the traces and the result structure we have. It is available in the OPC UA clients folder. And for any questions on usage of this simulator or reference examples, please feel free to contact us.